Hello, and welcome to a lecture on Aperture Theory. Here's the outline of this lecture. First, I'll give a brief overview of the equivalence principle. Then I'll discuss the application of the equivalence principle to apertures, and by this we mean antennas which can be described as apertures. These types of antennas fall basically into two categories. The first category is apertures in ground planes, and that might include slots, windows, things of that nature. The second category is apertures in free space. For example, here's a crude picture of a horn, and here would be the throat of the horn, maybe a coax feed back here. This opening is an aperture in free space. In other words, there's nothing over here, there's nothing over here, there's nothing over here. Similarly, reflector antennas can be described as apertures in free space, and phased arrays can be described as apertures in free space. For example, here is a square aperture. Perhaps it's filled with dipole-type elements. The approach we'll be using here will be similar to what we've done in previous lectures. We'll use the concept of electric and magnetic vector potentials to compute the radiated electric and magnetic field intensities. As you hopefully recall, we get the vector potentials by integrating over currents. In this case, we will have identified electric and magnetic surface currents which flow in the aperture. And those electric and magnetic surface currents will have been determined through the equivalence principle from the electric and magnetic field intensities in the aperture. So the idea is first identify electric and magnetic field intensities in the aperture, use equivalence to get equivalent magnetic and electric surface currents. From those surface currents, compute the vector potentials. From those vector potentials, compute the radiated fields. So that's the overall strategy. Now, there are many ways to apply the equivalence principle, so I'm going to adopt some terminology here. I'm going to call this particular type 1. Now, that's just my way of talking about it. Don't try to find this in a textbook somewhere. But just between you and I, as a technique for identifying the various ways to apply the equivalence principle, I'll use this terminology. So first I'll talk about type 1 equivalence. The scenario is as follows. We have a problem in which we have identified some surface, and inside the surface, that is inside the volume defined by that surface, we have sources and structures. And we know everywhere in this volume the fields E1 and H1, the electric and magnetic field intensities. Outside the surface, we have no structures or sources. So region 2 is a simpler region because it has no sources and no structures. And we also know the fields there, E2 and H2. And then finally, we define a surface normal, which points into region 2 as usual. So, here's the idea. You define some surface that surrounds the antenna. Now, the antenna is made up of sources and structures, so this is the surface S that we've just already identified. Using boundary conditions, the electromagnetic boundary conditions, we can find currents which produce the same external fields. And by this, I mean fields in region 2, but with zero fields internal to S. So the idea is we'll use the equivalence principle to replace everything inside the surface with zero fields, and then we'll have, as a consequence, equivalent currents which flow on the surface. So since the fields will be zero inside the surface, the sources and structures will have been removed from the problem, and those new equivalent currents will radiate as if they're in free space. So here's the idea now executed. We have the fields in region 1 required to be 0. We have the same fields in region 2 that we had in the previous problem. So in region 2, nothing has changed as far as the fields are concerned. But in order to make this consistent, now we must identify surface currents which resolve the equivalence. There are two boundary conditions, one on the electric field, one on the magnetic field, and here they are. The electric surface current, which we've been calling J sub S, is given by N cross the value of the magnetic field intensity on the surface, and the magnetic surface current, M sub S, is given by minus the normal cross the electric field intensity on S. Okay, there's a different way, or a supplementary way to describe this problem, and I'll call it type 2A. There will also be a type 2F that I'll show you in a moment, but this we'll call type 2A. What we do in type 2A is we take the previous problem, this scenario I just showed you here, and we make one additional change. Inside here, we'll replace that entire volume with a perfect magnetic conductor. Now that's a material that perfectly conducts magnetic current. Now we're allowed to do that because the fields in this region are 0. So if we add anything in here, we know that the fields will still the surface currents will be the same. In other words, there's no change to the problem if we now put things in this volume because the fields are known to be 0. So we're allowed to do that. When we add this perfect magnetic conductor, this is the new scenario. So we've started off with the type 1 equivalent scenario. Since the fields are 0 inside the surface, the one thing, we could do many things here, but one thing we can do is fill it with a perfect magnetic conducting material. And the effect of that is it shorts out the magnetic surface currents. So here we had these magnetic surface currents, but when we add the magnetic conductor, which we're allowed to do with no consequence to the fields out here, the magnetic currents are shorted out. Now we can do one more thing. We can invoke image theory to eliminate the material. So we invoked the material to get rid of the magnetic currents. Now we can apply image theory to eliminate that material. The electric current will double, the magnetic currents will continue to be gone. So here's the scenario that we'll call type 2A equivalence. Again, we end up with 0 fields inside the surface, inside the volume bound by the surface. The magnetic currents are gone because they were shorted out in the previous step. And after invoking image theory, I get now twice current density that I had previously. So that's where that factor of 2 comes from. It comes from having invoked image theory to get rid of the perfect magnetic conductor and get back to free space. So now I have a scenario in which fields E2 and H2 are due entirely to electric currents. And these electric currents are flowing in free space. So this is a beautiful situation because now I can apply the techniques I already know about to determine E and H radiated by these fields. And we will know that these are the fields that we started off with. These fields in region 2 have not changed anywhere in this analysis. In type 2F equivalence, we do a very similar thing, except instead of using perfect magnetic conductor, we use perfect electric conductor. When we do that, the electric currents disappear and the magnetic currents are unaffected. So we start off with the type 1 scenario. Since the fields are 0 inside the surface, we can add a perfect electrical conducting material inside the volume because the fields are 0 and nothing will change. This shorts out the electric currents on the surface. So now we're at this point. Now we invoke image theory to eliminate the perfectly conducting material. The magnetic current will double, electric currents will be gone. So this is a scenario we have no J, because of this previous step. M, those current densities are doubled because of image theory that was used to get rid of the perfect conducting volume. Note that the only difference between type 2A and type 2F is the currents that serve as the source of the fields in region 2. Once again, the fields in region 2 have not changed throughout this analysis. So now we want to apply these ideas to large antennas. If we directly apply type 1 or type 2A or type 2F, as shown in the previous slides, that requires knowledge of the electric or magnetic fields over an enclosing surface. Now let's just think about that for a second. For a directive antenna, and in order for a directive antenna to be directive, it must be large. This is pretty awkward, or it might be impossible. Let me show you some examples. Here's a reflector antenna, or at least a very cartoonish version of a reflector antenna. Here's an aperture array. All right, I might try to draw it in 3 dimensions. So there's a rectangular aperture. Here's a horn, or a waveguide. That's what WG is. In these 3 cases, the fields are very hard to predict or measure except directly in front of the antenna. In other words, for a horn, it's pretty easy to know what the fields are right here in the aperture, the radiating aperture of the horn. Similarly, in an aperture array, it's pretty easy to know, or we can at least estimate, what the fields are in the aperture. In a reflector antenna, it turns out, we'll see this in a later lecture, it's pretty easy to know what the fields are in an aperture directly in front of the reflector. So in other words, if I have some feed here, it illuminates the reflector, those rays get bounced back into some aperture, and then I can define an aperture here where I know the fields. It's pretty easy to calculate them. So for each one of these 3 antenna types, I can find at least good estimates, if not exactly, the fields in some aperture in some region, but it's very difficult to know what the fields are out here. For an aperture array, it's very difficult to know what the fields are out here. For a reflector antenna, it's very hard to know what the fields are out here. That makes it hard to come up with a surface over which we know the fields and can apply the equivalence principle. Now, if we have an aperture in a ground screen, we have the problem that we can't get behind it. In other words, how do I draw a surface like that bounds the aperture? How do I know what the fields are out here? So even the simplest possible aperture antenna, which is just a opening cut into a ground plane, I have a problem applying this principle. So here's what we do instead. We enclose the half space. Let me explain what I mean by that. So for the simplest possible aperture, which is just a ground plane, that's this dark line here, with an opening in it, I'm marking the opening, what we do is we enclose the half space. In other words, our S is this dashed line that I'm showing here. The surface includes as part of the surface a flat area which is flush to the ground screen and flush to the aperture. And then the rest, in order to close this surface, I have this dome-like structure. So you can think of this as half a sphere, where I take a sphere, I cut it in half, I take the flat part that emerges after I cut the sphere in half, and that flat part fits flush to the ground screen. So one portion is flush to the surface. This other portion, the dome-like portion, what I do is I push that off to infinity in all directions. So in other words, I make the radius of the sphere infinite. Now, the reason for doing that is I get to apply then this electromagnetic principle known as the radiation condition, which simply says that we expect fields from this radiating aperture, or any bounded region of space, to go to 0 as the distance from the source goes to infinity. And if those fields are 0 to a good engineering approximation, then the associated equivalent currents will be 0. So the value in doing this, of making this surface go to infinity, is that we can then say everywhere on this part of the surface, those fields that result from the aperture over here will go to 0. Okay, so now let's take that idea and apply type 2F or type 2A equivalence. We obtain equivalent electric and magnetic currents, which are non-zero, only on the planar surface, because we said that the bounding dome-like structure, the fields were 0, so the equivalent currents are 0. But on the part that's flush to the aperture, or to the ground screen, now we have the potential for non-zero fields, and therefore non-zero equivalent currents. Now, certainly, the currents directly in front of the aperture, these here, right in front of the opening, or right on the opening if you want to think of it that way, they're going to provide the dominant contribution to the fields in the right half space. This is clear. Now, the currents that are not in the opening, that are a part of the surface, which corresponds to the ground screen, we can be pretty sure that they're going to be weak. Now, they may or may not be negligible, and I'll tell you that this is not rigorous, assuming that they're negligible, but it's usually a pretty good engineering approximation. So given that there's some caveats to this idea, I'm going to identify it with a number here so I can use this number to remind you of what I'm talking about. And so the only currents we have to worry about are these, the ones directly in the aperture. So this aperture approximation simplifies the problem to that of just finding the fields on the bounding surface that we've defined directly in front of the aperture. In other words, all we have to do is identify what's going on in this part of the problem, in the aperture. If the aperture is electrically large, then the fields in the aperture will be approximately the same as the fields incident on the aperture from the left half space. What do I mean by that? Well, if we have some source back here and it's creating a wave, well, I can think of what happens right here. In other words, I can identify the incident electric and magnetic fields. I can call those E super I and H super I. And using the normal analysis principles, I say that those incident fields are the ones that exist in the absence of any structure or any scattering. In other words, they're simply due to the sources, as if they're in free space, isolated from everything else. So I can identify fields that are incident on the aperture, and then I can make the approximation that the fields that actually exist in the aperture, the total fields, is what I'm talking about here, incident plus scattered, will be about the same as the incident fields. Okay? So what I'm doing here is I'm assuming that whatever fields exist in the aperture are overwhelmingly determined by the fields incident, and that any scattering, say from the edge of the aperture, is negligible. Okay, so since this is not a uniformly valid approximation, there may be some caveats, may not always be true, I'll identify it with a 2 with a box around it. Now, the difference between this, the fields in the aperture invoking this assumption, and the truth, which is the total fields that include the effects of the aperture, the difference between those two things is that the actual fields in the aperture is the sum of the incident fields and the fields diffracted by the edges of the aperture. If the word diffracted seems weird to you, just think scattered. All right. So throughout the rest of this lecture, we're going to assume that that scattering, diffraction, is not important, and then in subsequent lectures we can clean that up a little bit, or at least we'll come up with methods to allow corrections to this. So for now, we'll assume that diffraction is relatively weak, and we'll just neglect it. Now, how reasonable are those assumptions, 1 and 2? Well, this depends on the size of the aperture relative to a wavelength. Let's say D is the maximum dimension of the aperture. So for example, if we have a circular aperture, d is the diameter. If we have a square aperture, d is the side length. That definition really isn't critical, but just to give you some idea. Let me define a parameter, kd. Now remember, k is wave number. That's 2 pi over lambda. All right? So we can make that substitution, and we can pull out the 2 pi. Kd, you see, is just a way of talking about the electrical size of the aperture. In other words, d divided by lambda is how many wavelengths across the aperture is. So kd is just proportional to that. So we like to use this notation here as opposed to this notation here because this is a little bit more compact. So I'm identifying this just so you aren't confused by this later. Now, if kd is large or becomes very large, so maybe 10 wavelengths, maybe 100 wavelengths, so on, then these approximations become very, very good. In other words, if kd is very large, that means the opening is a large number of wavelengths across, then the scattering by the edges into the aperture is small and can normally be neglected. So we refer to this as asymptotic high frequency conditions. This is high frequency because as the frequency goes up, the wavelength gets small, so this thing gets big. Saying that the frequency has become very high is same as saying that the aperture has become electrically very large. And if that's the case, then 1 and 2 are reasonable approximations. Now, if kd is not large, but rather it's reduced and it becomes comparable to a wavelength, we might say it this way, if it's on the order of a wavelength, then this turns out to still be relatively good approximation. We have to be careful, but it's not a crazy thing to do. And one way to see this is through observation. I wouldn't even call it a principle. I'd call it an observation, but it goes by the name of Huygens principle. I'll just give you a very brief idea of what this principle works like. So Huygens, in centuries past, thought about apertures and realized that the fields radiated from an aperture could be calculated as as if they were from a series of point sources or a collection of point sources in the aperture. So what he did is he identified a continuum of point sources in the aperture, and since they're point sources, they radiate spherical waves. So each one of these point sources radiates a spherical wave. You discover that this collection of point sources, each radiating spherical waves, when added together, gave you the actual radiated field out here that you would expect. So this is probably not so obvious yet, but we'll do some investigation later, and we'll see that this is in fact a good idea, that as the aperture dimension even gets down to about a wavelength, this is still a pretty usable idea. An approximation to be sure, but a useful one. Okay, now we've identified 3 types of equivalence: type 1, type 2a, and type 2f. Now, it may seem at first glance that type 2, either A or F, should be chosen. Why do I say that? Because in type 1, we had both J's and M's. So type 1, we had both J's and M's. In type 2a, we had just J's, and in type 2f, we had just M's. So it seems like it's less work just to use type 2, either A or F. And that much of the idea is true. But the best choice is not always so clear. And the reason the best choice is not always clear is because, remember, we're going to invoke approximations. Those approximations 1 and 2. So it's not clear that once we make the approximations that all 3 of these methods, all 3 of these equivalences are going to work equally well. There's some wisdom on this that's pretty well established. I think in most sources you read, most textbooks, you'll just see it stated as the way to do it. I don't think it's necessarily clear that that's the case, but there is some good evidence that this is the way to go. So let me show you how to sort this out. If you have an aperture and a ground plane, for example, the things I've been showing in the previous slides, in general some window or some opening in a planar ground screen, then normally you'd use type 2F. In other words, the one that gave you magnetic currents. And this is because the introduction of the perfect electrical conductor allows the invocation of image theory, and it's closer to physical reality. In other words, what you're doing to come up with type 2F corresponds more closely to the actual physics of the problem. Now again, if we don't invoke approximations 1 and 2, this isn't a problem because equivalence is equivalence. However, if we're concerned that approximations 1 and 2 are going to create differences between these three types of equivalence, then in the case of an opening in a screen, we normally like type 2F because that seems like it's closer to what's actually happening in this problem. For apertures in free space, for example, when we use this technique to model reflectors and phased arrays, as I demonstrated on a previous slide, then typically we use type 1, both electric and magnetic currents. Type 2A, by the way, that's just electric currents. That's typically chosen for scattering problems. You may be familiar or may have heard previously of a technique known as physical optics. Physical optics can be done a number of ways, but normally in engineering electromagnetics, it's done using what I would have called a type 2A equivalence. You have just the J's. So there's the usual selection process. Now, we'll continue in this lecture talking about apertures, so we're just going to consider this case. This is for a future lecture. All right, so let's talk about radiation from planar apertures. In other words, let's solve that problem of an aperture in a planar ground screen. Now, if we use type 1 equivalence, right, which is always usable, there's no question about that. We're going to simplify it to a type 2 thing later. But type 1, if we just work it out, what that looks like. Well, here is the expression for the magnetic vector potential, which hopefully you recognize from a previous lecture. And remember, this is for the far field condition. Here is the magnetic current density, right? It's just N cross the magnetic field intensity in the aperture. So we make that substitution. Here's J, and now there's N cross H. N cross doesn't change with the integration. N cross is always the same at every point in the aperture, so we can pull that out of the integration. And then what we're going to do is we're going to take this integral here and we're going to give it a name. And the name we're going to give it is Q. Now, that's a vector when we're done integrating, so we have to identify it as a vector. So this is the resulting magnetic vector potential. Now, this Q, if you look at the expression carefully here, you will recognize this, or perhaps you'll recognize this, as a spatial Fourier transform. All right? If you've never dealt with two-dimensional Fourier transforms before, that's okay. You know that a one-dimensional Fourier transform converts, for example, time domain expressions into frequency domain expressions. Well, here, what we're doing is we're converting the fields in the aperture, right, to some other domain. It just happens to be the form of a Fourier transform. I'll have some more to say about that at the end of the lecture. But it's useful to know that this quantity Q turns out to be the spatial Fourier transform, two-dimensional, of the magnetic field intensity in the aperture. Now for the electric vector potential, here's the expression, again a far field expression. Here is the expression for the magnetic surface current density, minus N cross the electric field intensity in the aperture. Then M is replaced with that expression. N cross doesn't change with the integration. And I have an integral here, which I'll name P. So here's P. So here's a simplified expression, and this is F. And guess what? P turns out to be the spatial Fourier transform of the electric fields in the aperture. So we find that the magnetic vector potential is obtained by computing the spatial Fourier transform of the electric fields in the aperture. You take n cross of that quantity, you apply a spherical wave function, and then minus epsilon. Now, let's think a little bit more carefully about this, because there's some simplification possible. Let me attach a coordinate system to the ground screen. So in this coordinate system, x is in the ground screen, or in the ground plane. Y is in the ground screen, right? And then z is perpendicular to the ground screen. So in this coordinate system, then n, or n hat, is equal to z hat, and x hat and y hat lie in the plane of the aperture. You'll notice, once you set up the problem this way, that the normal components of the fields in the aperture don't contribute. What do I mean by that? Any component of the magnetic or electric field in the aperture, which has a z hat component, well, when I take n cross that component, I'll get 0, because the cross product of any two vectors that point in the same direction is 0, right? In other words, the cross product between two vectors is proportional to the sine of the angle between those vectors. So when the vectors point in the same direction, sine theta is 0. So it's clear that we will not need to compute the z components of the spatial Fourier transforms for that reason. So this is the expression I came up with before for the magnetic vector potential. Now I know that Q has no z hat component, so I'll just write out the rest of it, and I'll take the cross product with respect to the normal. And so what I'll get after taking that cross product is minus x hat of the y component of the spatial Fourier transform plus y hat of the x component of the spatial Fourier transform. Similarly, with the with the electric vector potential, I get minus x hat of the y component of the spatial Fourier transform plus y hat times the x component of the spatial Fourier transform. So the reason I do that is because now we can see some simplified expressions. So let me work this through. The electric fields resulting from these equivalent electric currents, because they're from electric currents, I'll use subscript A here, we know can be calculated in this way. This is the far field approximation again. Remember this. This is for the far field condition. And I can now work through this relatively quickly. This is a great exercise for you to do. I don't want to go through it step by step because it would take up 3 or 4 slides. But it's straightforward math, and I think you should do it to make sure that A, I've got the right answer here, but also B, that you can see, it'll confirm that you actually understand how these quantities work. When you do this, when you take this expression, evaluate it out, using the expressions I've worked out in the previous slides, you find that the electric field intensity due to that equivalent electric current is plus jk eta. There's our spherical wave component. We get a cosine theta, and then we get this stuff. We get a theta hat component and a phi hat component. The theta hat component is given by this. The phi hat component is given by this expression, and then just repeating, Q sub x is the x component of the spatial Fourier transform. The y component, the Qy is the y component of the spatial Fourier transform in this case, and so on. For the fields arising from the magnetic equivalent currents, I can calculate them this way. Again, a far field condition expression. And what I get using the same kind of analysis is a very similar looking expression, but now in terms of P's, because the P's are related to the magnetic currents. By the way, not only should you work through the math and confirm that you can get these expressions, But also, you could do a quick check through dimensional analysis, and I would encourage you to do that. Check and make sure the units make sense all the way through this. And then finally, if I want the complete answer using type 1 equivalence, I have to add the results that I get for the equivalent electric currents to the result that I get from the equivalent magnetic currents. I add them up, and that's the total field. Now, for an aperture and a ground plane, we would normally handle that using type 2F equivalence. What I just worked out was the general case, or type 1. Type 2F, invoking expression, these approximations I talked about before, the electric field is 0, resulting, at least the electric fields resulting from electric currents, because we made those go away. The electric fields resulting from the magnetic currents, which remain, are given again by this expression. And here it is again. And note now, we have a 2 instead of a 4 here. On the previous slide, we had a 4 in that position. The reason there's now a 2 is because in type 2F, we get from image theory twice the magnetic current density. So when we pull that factor of 2 all the way through, it cancels with this, or partially cancels this factor 4 here, and we get a 2. The reason I point that out is because I find over and over again a factor of 2 errors in work, and it's because you have forgotten this fact. And then the total fields, of course, are the fields due to the magnetic equivalent currents, because those are the only ones that are present in type 2F equivalence. Now, apertures in free space, as previously mentioned, these are ordinarily handled using type 1. And we already have those equations. That's what I worked out previously. However, it's often valid, again, we're getting ready to make another assumption here, that the source of the equivalent currents is a normally incident transverse electromagnetic plane wave. So what we're doing here is we're assuming the fields incident on the aperture from the backside, if you'd like to call it that, are normally incident. So in other words, EI and HI look like this. They're plane waves which are normally incident on the surface. They're not spherical waves. They're not approaching from some oblique angle. They look like this here. Now, in that case, these are plane waves, and I can relate E and H through the plane wave relationship, right? That's hopefully something you already know about. And through the plane wave relationship, then, the magnetic field intensity in the aperture is given by 1 over the intrinsic impedance of the medium and cross the electric field in the aperture. So in this case, the quantities Q and P are also related by the plane wave relationship. Right? Now I'm saying this, and maybe you see this right away, or maybe you have to go back and do a little math to see this. All right, so once I see this, then I can immediately relate the x and y components of those two spatial Fourier transforms. For example, I can see that qx, the x component of q, is related to the y component of p through this relationship. And similarly, the y component of q is related to the x component of p through this relationship. Again, this falls out directly if you assume that the fields in the aperture satisfy the plane wave relationship. And by the way, I may have said before that I'm assuming that this is normally incident, but even that can be relaxed. This also works if you have a plane wave, but it's arriving from an oblique direction. So just to be clear. Now, if I recognize these relationships, and I include them in the previous expression I came up with, now I find the electric field is well approximated as this new quantity. And this is now type 1, right? Even though you only see magnetic current contributions here, it's type 1. And what happened is the electric currents went away because I've related those two types of currents through the plane wave relationship. So I end up with plus jk, here's my spherical wave, times 2, so that 4 here becomes a 2. I get this thing, 1 plus cosine theta over 2. By the way, in some future lecture, we'll probably give that a name. The name we'll give it is the obliquity factor. So just so you know that's coming. And then I have a theta hat component and a phi hat component, and they're described completely in terms of the spatial Fourier transforms of the magnetic current intensity distribution in the aperture. Okay, so why bother with this thing I did on the previous slide if unmodified full-blown type 1 equivalence is okay? Fair question. In other words, why make an approximation if you don't have to? Well, here it's simpler, so you don't have to compute Q. This is valuable in engineering work because if you can do a simpler analysis and you know it's approximately the same as a more detailed analysis, you're less likely to make a mistake because the analysis is simpler, and that's not a bad idea. So why do something more complicated than you have to and take the increased chance of making a mistake? There is some savings in computation time, right? We have effectively reduced the amount of work by 2, a factor of 2. So this could be important. If you have electrically large apertures, you've saved a factor of 2 in computation. I'll tell you, as of the year 2016, this argument really is not as compelling as it used to be. 2 decades ago, this was an important issue. Nowadays, even very large apertures can be done kind of brute force, and so this argument really isn't as compelling. This one still is, that it's simpler to compute and you're less likely to make a mistake. How good is this approximation? Let's say you like this and you want to use it. You should know something about how good the approximation is. Well, let me identify a few issues here. One is it's very good near broadside, right? So, for example, let's say you have this plane wave incident on the aperture, and now the aperture is radiating. It turns out for some zone defined by this angular extent here, that approximation is excellent. But as you get further out in this direction, less good. So as you approach grazing angle, for example, it's not as good. But there are other things going wrong there as well. So because we're also making this approximation 1, approximation 2. So there's other reasons why we wouldn't put too much confidence as we got further and further away from broadside. For focused paraboloidal reflectors, in other words, you have something like this, and the reflector is making a very narrow beam that looks like this. Certainly around the main lobe, for main lobe work, this is pretty good. For phased arrays, same thing. If you have a main lobe and you're doing this approximation around the main lobe, this is pretty good. Obviously neglects finiteness effects, so in a reflector problem, you have diffraction from the edges. That's being neglected. We're going to have to clean that up, but you may or may not have to actually do that. Certainly dangerous or invalid away from broadside, as I pointed out here. Almost always good enough to use for initial design, after which unmodified type 1 equivalence could be used to verify the result. So if you're doing this to improve computational efficiency, then one strategy is to do this cruder approximation to get the design kind of initialized. And once you kind of feel pretty good about a design, then you could do the unmodified type 1 equivalence, not making the plane wave assumption here, and see what you get. Okay, so now it's time to wrap up. A broad class of antennas, these things we call aperture antennas, can be described as apertures having dimensions on the order of a wavelength or so or greater. So this includes apertures in ground screens, slots, windows, whatever you'd like to call them. Apertures in free space, so things that are not necessarily apertures precisely, but can be modeled as apertures. So phased arrays and reflector antennas like dishes, and I should also add horns. Those are all apertures in free space. and these techniques apply. The fields radiated by these antennas can be determined by applying a spatial transform of the fields in the aperture. So what we identified, or an important result from this lecture, was that we have these quantities P and Q. So we take a spatial Fourier transform of the fields in the aperture. Turns out that those are the things which then determine the radiated fields and then the pattern. So a new idea here, and this is what I'll conclude the lecture with, the reverse also works. In other words, one can take the inverse Fourier transform of the radiation pattern to determine the fields in the aperture that give rise to that pattern. In other words, we have these equivalent currents, J and M, and we take a Fourier transform, that gives us P and Q, and we can think of these as being a pattern. We can therefore take the inverse Fourier transform and get the equivalent currents. So if we know a pattern, we can specify it somehow, take an inverse Fourier transform and get the currents which give rise to that pattern. So that'll be an idea that we will certainly follow up on, and it'll be a useful way to design phased arrays, for example. This concludes this lecture on aperture theory.